In the early 1990s, a new kind of bridge suddenly appeared, seemingly out of nowhere. It's this bridge. It's the Alamillo Bridge in Seville, Spain. It's designed by the Spanish architect-engineer Santiago Calatrava. It was completed in 1992, and if this bridge looks familiar, it should, because we've been seeing this sort of thing all over the place in the last 25 years. So how did this bridge type suddenly spring out of nowhere and become the preferred bridge of everyone seemingly everywhere? You can't swing a cat without hitting a bridge that's leaning over on its side with a bunch of cables hanging off of it. Well, that's the question for our big idea design case study on the Alamillo Bridge, which is Santiago Calatrava's first foray into this sort of bridge design. So in order to do this, we're going to have to talk about different kinds of bridges. There are some pretty familiar types. There are beam bridges, the simple sort of straight beam across whatever you're trying to bridge, as the name would have it. There's cantilever bridges, there are arch bridges, there are suspension bridges, there are cable-stayed bridges, which look a lot like suspension bridges, and then there are truss bridges, like we're familiar with from railroad tracks. And what we're going to do now is look at the difference between the suspension and the cable-stayed bridges, because this is really where Santiago Calatrava's bridge emerges. So the Golden Gate Bridge, for example, is a suspension bridge. In a suspension bridge, the cable stays are continuous all the way across the span between the two piers or pylons. A different kind of bridge would be the Brooklyn Bridge, which is actually a hybrid between a cable-stayed and a suspension bridge. And if you look closely at the image, you can find that the cable goes all the way between the two towers, making it a suspension bridge where the deck is hanging, but also the cable stays are coming diagonally out from the pylon itself, which means the pylon is holding up any given point of the decking of the bridge. So a typical cable-stayed bridge, or a pure cable-stayed bridge, has exactly this characteristic. There are pylons. The pylons have the cables that come off, and it's the cables attached span between the pylons and the bridge deck itself that are keeping the bridge level. So in this example, we have a double span. We have two pylons out in the opening, in this case a body of water, and the cables don't touch in the middle. Each one is clearly tied to a particular pylon, and that's what keeps that bridge up. Now, if we were to reduce the number of pylons on the bridge, we'd have a single pylon, but you'll still notice that there is a pylon pretty much in the center of the span. And this is fine if you have enough distance to do it. In fact, it's the cable-stayed bridges that can make quite a span because of the way that they're designed. But let's imagine that we have a case where we don't necessarily want to put a pylon in the center of the span. So if we can't do that, we wind up with something else. We wind up with what's called a cantilever spar cable-stayed bridge. It's cable-stayed in the sense that the cables are spanning between the deck and the pylon itself, and it's cantilevered in the same way that, for example, a balcony or an overhang is cantilevered, which means that there is a long, strong piece that is embedded in something. In this case, it would be embedded in the ground. In the case of a balcony, it's embedded in the building, which then sticks out, and it's its own material strength that keeps that thing stable. So it's what keeps your balcony from sagging, for example, or here the pylons of the bridge from sagging. Well, you can imagine that there's a lot of force coming down onto that pylon from the bridge, which wants to sag. And so it would make some sense then, if you were to think about that force as pulling down and pulling, trying to overturn the pylon itself, it might make some sense for us to then simply to angle or lean that spar or pylon back in order to counterbalance the weight of the bridge decking itself pulling down. And this, of course, should begin to look very familiar, because this is exactly the picture of the Alamillo Bridge. It's a cantilever, spar, cable-stayed bridge. So this story makes a lot of rational sense, but I wonder if there isn't a little bit more to it. Well, in order to figure that out, we're going to have to talk about the designer, Santiago Calatrava. Calatrava is born in Spain, living in Switzerland. He has a degree in architecture from Valencia in Spain, and also a second degree in civil engineering from the ETH in Zurich. So he is combining both architecture and civil engineering as part of his work. And we can look at some contemporary projects that Calatrava is well known for in building. So we have the Turning Torso, a tall apartment building in Malmö, Sweden. The Milwaukee Art Museum is quite famous for its flying wings like a bird opening and closing. We also have the Tenerife Auditorium, again, a very sculptural form, somehow also reminiscent of birds. And these things all bear some similarities. They're clearly from the hand of one particular designer. And let's try to find out a little bit more of what the inspirations behind those projects might have been. So the Tenerife Auditorium, for example, you can see bears a strong similarity to the sculptural works that Calatrava also does. So he's exploring forms, and then these forms are enlarged and become the shells of buildings, which are then made of concrete. And so it's his structural engineering prowess in the use of reinforced concrete that allows him to achieve the same structural forms that he is exploring through his sculpture work. Similarly, the idea of the opening and closing wings of the Milwaukee Art Museum are born, on the one hand, they look a lot like birds, but as it turns out, they're not actually birds. They have something more to do with another interest of his that is in moving buildings. And you can see here in his sketchbooks, the analogy is not to a bird, but rather to a hand that opens and closes and becomes an inspiration for his architectural work. Or in the example of the Alamillo project, there is a human torso. We can see a sculptural model tied very closely in his sketchbooks to a sketch of the human torso. Once we see the models and the sketches together, we suddenly realize where the Malmö building is coming from. So there's the logical path, but it seems like there's something more. Calatrava is clearly a rational architect and a rational civil engineer, and we can put two and two together to figure out deductively how a better bridge design might work. But we can also see that there are other aspects to his personality that are somehow informing the kinds of projects that he develops. And that's really the question to ponder here. How do these unique forms of Santiago Calatrava, including the Alamillo Bridge, come into being?